it is very unlikely that my theory is correct. That fact is not lost on me, strictly because of the nature of who I am and what I'm doing. But I'm an independent researcher with no experience in general relativity, no real academic experience in general relativity, and yet I want to propose this theory, which I say can probably link general relativity to string theory, can explain a number of bizarre behaviors throughout the cosmos, such as dark matter and dark energy, and may provide a model for the Big Bang. These are a lot of very extraordinary claims from someone who does not appear to have any of the ability to do so. So even I come back and I say, Ben, what in the world do you think links you to this theory, keeps you going on? Most of my videos are about trying to convince someone else, hey, try to look into the theory my way. But what keeps me coming back? And to me, it's the law of general covariance. Physical laws are invariant under arbitrary coordinate transformations. What I'm going to do here is I'm going to have the Schwarzschild metric. This is the solution for a spherical mass, really any spherical mass, but the numbers get very interesting as 2m approaches r. With this coordinate, you can see it goes to 0. With this coordinate, it goes to a singularity, and these two coordinates don't really compute for anything interesting. So let's focus on these two coordinates here. This is basically my time coordinate, and my time coordinate is heading to 0. So that means that the physical nature of space-time means that time comes to a stop. And physicists have proposed, oh, we change this. We can change this point of view of it by making a coordinate transformation to the Kruskal-Sechs or the Eddington-Finkelstein, or I saw a very good transformation done by Dirac in his paper. And that's all well and good, and I can't say that any coordinate transformations are wrong. But what I can say is that if you transform the space, you're not going to transform out of time vanishing at the event horizon, because that's a physical law. It is a physical law derived directly from the Schwarzschild that you will have time vanish at the event horizon. That's what keeps me coming back, because I know I can't transform out of this because of the law of general covariance. And yes, this does become a singularity, and that's problematic in a mathematical sense. It's important to remember that singularity is a mathematical term. There's been an awful, horrible hijacking in which singularity has become a term in physics, and I don't think that's correct. I think it should be a strictly mathematical term. Just like tensor is a term for something that can be transformed as in tensor transformations. It's very difficult for me to define what a tensor is without saying tensor transformation, so it's almost a tautology that I'm saying a tensor is a tensor because it's a tensor. But, in any event, the term singularity, in my opinion, is not something, it's something that should be reserved for mathematics that applies to physics. This singularity at the event, below the event horizon at the center of a black hole, it's important to know that when you say singularity, you're not talking about something physical. You're talking about something mathematical, strictly mathematical. And with this singularity, of course, it can be removed. It's just a coordinate singularity. So you can do a transformation, you don't have to worry about it anymore. And I'm fine with that. I'm absolutely fine with being able to transform away singularities, because that's math. But when it comes to physics, when it comes to the nature of what's going on in the space around black holes, I don't think that there's any way to escape this term. This term goes to 0. It doesn't matter how you transform it. The physical nature of that term going to 0 means that there's no crossing the event horizon. So I'm just going to doodle very quickly. I have an event horizon here. And I know that time will be infinite at the event horizon. Or rather, the durations of time will go to infinity. And I have, time less than infinity above the event horizon at all times. So I know I'll always have less than infinite time above the event horizon. And I'll always have exactly infinite time at the event horizon. So I know, by the law of general covariance, that it doesn't matter how I transform the space, my particles will be excluded from the event horizon because it takes an infinite amount of time to reach the event horizon. And the law of general covariance gives me absolute assurance that no matter what happens, no matter what transformation I do, what transformation I perform, or how I want to propose that they operate, I can introduce two new functions and two new variables, and I could completely rearrange the coordinates, and I have a working coordinate system. This is what Dirac does in his paper. And there's no singularity at the event horizon. Wonderful! Wonderful coordinate system. But it doesn't change the physical law of time vanishing at the event horizon. That is a physical law of nature. So that is what keeps me coming back to my theory. There's many more wonderful things that emerge from this theory. And I'm most intrigued by asymptotic darkness, which is a process that was discovered by a physicist. His name escapes me right now. But as it would happen to have occurred, I independently drew up the same conclusion, just working with my black hole model. And that reassures me that I'm on the right path. And the stepping stone, the starting stepping stone for that path is right here in the law of general covariance, saying that I know for a fact time will go to infinity at the event horizon, and there's not a single coordinate transformation that will ever change that, because that's the law of general covariance.